Recursive partition cosmology. A unified first principles framework for emergent geometry, thermodynamic spacetime, and quantist inertia. Chris D. Seeley. Independent researcher, Canada. Correspondence. Preprint Draft 1.1, May 2026, submitted for peer review. Abstract. We present a unified first principles framework in which geometry, curvature, entropy, inertia, and temperature emerge from a single primitive operation, recursive conserved partition of a normalized substrate U equals 1. No spacetime manifold, metric, or dimensional coordinates are assumed. Instead, recursive division generates distinguishable partition states whose incompatibilities produce defect structures, harmonic exclusion zones, curvature, vortices, and emergent rotational dynamics. Entropy emerges from distinguishable state counting. Curvature emerges from partition tension gradients. The golden ratio phi arises as the fixed point of the simplest recursive ratio. Pi squared emerges as the closed surface inverse square projection penalty of any thermal bounded system. Temperature is identified as the local partition update rate. The Howard elastic field Xin is derived as the compression of the recursive attractor under closed surface thermal projection. Quantist inertia is recovered as the large-scale limit of horizon-constrained partition mode availability. The framework predicts a specific, immediately testable result, the ratio of observed to QI predicted rotation curve break radii across a galaxy sample equals squared, where C2 is the second sound velocity of the cosmological superfluid. A solar system scale quantum interferometric array using Beck-Maser stations at Lagrange points is proposed as the primary experimental apparatus. The framework is incomplete, 11 specific outstanding derivations are identified but as internally constrained, falsifiable at each stage, and grounded exclusively in established physics and mathematics. Keywords: recursive partition, emergent geometry, quantist inertia, superfluid cosmology, holographic entropy, Bekenstein bound, elastic coupling field, Beck-Maser interferometry, Lagrange point array, second sound, thermodynamic spacetime. 1.1 The starting point, U equals 1. The framework begins from a single normalized conserved substrate with no assumed structure. 6 primitive constraints are imposed. These are not assumptions about physics, they are logical requirements for any framework that derives rather than assumes its structure. 1. Exact global conservation. The total substrate is invariant under all partition operations. 2. Recursive division is the only primitive operation. 3. No pre-existing geometry, metric, or coordinate system. 4. No infinitesimals, all partition states are finite. 5. Entropy emerges from counting distinguishable partition states. 6. Stable structure requires harmonic exclusion zones where recursive packing fails. 1.2 Recursive partition operation. A local partition operation divides a state UI into n equal substates. Global conservation is maintained exactly. Recursive partition produces distinguishable informational states. This establishes the first primitive relational structure, not spatial, not temporal, but informational. 2 partition states are distinguishable if and only if their values differ. Distinguishability is the precursor to all subsequent structure. 1.3 Emergent entropy. Shannon entropy emerges immediately from distinguishable partition state counting. This is the first derived result. Entropy is not fundamental. It is a count of distinguishable configurations of the conserved substrate. The second law ds, dt greater than equals 0 follows from the monotonic increase in distinguishable states as recursive partition depth increases. There is no operation that merges distinguishable states back into indistinguishable ones without external constraint. Entropy is therefore the only irreducible asymmetry in the framework. All other asymmetries, including the arrow of time, the directionality of gravity, and the preferred orientation of angular momentum, are downstream of entropy, not upstream of it. Entropy H equals sum pi log 2 is derived from recursive partition state counting. The second law ds, dt greater than equals 0 follows from partition irreversibility. Entropy is not a property of a pre-existing space. Space is a property of accumulated entropy gradients. This inverts the standard model's ontological order. Part 2: Emergent geometry from partition frustration. 2.1 The harmonic development sequence. Recursive partition at increasing depth generates geometric structure. The sequence is not postulated, it is the necessary consequence of attempting to partition a conserved substrate into progressively finer distinguishable states while maintaining global conservation. At each recursive depth n, the system generates the simplest stable configuration compatible with the accumulated partition constraints. 2.2 Why n equals 5 produces frustration, the tetrahedral packing failure. The dihedral angle of a regular tetrahedron is 70.53 degrees. 5 tetrahedra sharing a common edge subtend 5 times 70.53 equals 352.65 degrees, leaving a 7.35 degree gap that cannot be filled by another tetrahedron. This is not a failure of the framework, it is the framework producing its first non-trivial result. Perfect recursive packing is impossible in 3D space from tetrahedral units. The frustration is real, necessary, and structure generating. This frustration produces 3 consequences that drive all subsequent physics. Defect structures, local regions where partition incompatibility exceeds the stability threshold and stable packing fails. These are not mathematical failures but physical objects, stable, persistent, topology-carrying structures. Harmonic exclusion zones, regions where recursive packing is forbidden by the accumulated tension. These holes are stabilizing, not pathological. Perfect packing produces brittle rigidity and catastrophic stress propagation. Defects permit elasticity, distribute stress, and prevent recursive collapse. Quasiperiodic organization, the system adopts the densest possible packing consistent with the tetrahedral constraint. This is Penrose tiling in 2D, icosahedral quasi-crystal structure in 3D. The golden ratio phi appears here as the natural spacing ratio. 2.3 Why phi equals 1.618 is the natural recursive attractor. The golden ratio phi satisfies the fixed point equation of the simplest possible recursive ratio. In the partition framework, phi appears because it is the ratio between successive partition states that minimizes interference between modes. Any recursive system that seeks to maximize distinguishable states while minimizing cross-coupling between them converges to phi spacing between modes. This has been independently confirmed in 3D magnetohydrodynamic fluid simulations. Phi and 1, phi appear as stability attractors in coupled fluid electromagnetic systems, not because they are inserted but because the boundary conditions select them as lowest interference stable modes. Phi is therefore not a fundamental physical constant. It is the mathematical fixed point of recursion, the attractor toward which any system minimizing partition interference converges. Its appearance in physical systems is a consequence of that convergence, not evidence of phi having special ontological status. 2.4 Emergent curvature from partition tension. Partition incompatibility between adjacent states is defined as the mismatch. This aligns the framework structurally with Sakharov's induced gravity, Verlin's entropic gravity, and Jacobson's thermodynamic derivation of the Einstein equations. In all these approaches, spacetime geometry is not fundamental but emerges from underlying microphysical degrees of freedom. The partition framework provides a more primitive starting point than any of these. Partition tension gradients precede the thermodynamic quantities those frameworks begin with. Outstanding derivation OD1 required. Show that in the continuum limit, the discrete tension gradient grad converges to a continuous curvature tensor K mu satisfying the contracted Bianchi identities. This is the connection between the partition framework and general relativity. Until this derivation is complete, K proportional to grad is a structural correspondence, not a derived result. Part IIB incommensurability as the generator of physics, from SQRT to spacetime. The partition framework's central result, that geometry, entropy, and time emerge from recursive partition incompatibility, has a precise mathematical antecedent that can be traced through dimensional progression. The same incommensurability that appears as the irrationality of SQRT in one dimension reappears as the tetrahedral packing gap in 3 dimensions. As the Pythagorean comma in frequency space, and as the elastic coupling field x less than 1, phi in the partition substrate. These are not analogies. They are projections of the same structural fact into different domains. 2b.2 The Pythagorean comma and the 7.356 degree gap, same structure. The connection between the spatial gap and the musical comma is not metaphorical, both arise from the same number theoretic fact. The connection between the spatial gap and the musical comma is not metaphorical, both arise from the same number theoretic fact. Both gaps arise from the statement, you cannot solve a p equals b q with integers unless a and b share prime factors. In 3D space, 5-fold symmetry requires SQRT, which is irrational. In frequency space, the circle of fifths requires prime 3, which cannot generate prime 5. The 7.356 degree gap is the spatial shadow. The 23.46 cent comma is the frequency shadow. The elastic strain in the partition framework is the spacetime shadow. The Howard comma, the gap between the ideal recursive attractor 1, phi and the realized physical coupling x, is the dynamic version of the same structure. It does not close because it cannot close, the underlying incommensurability is irreducible. The partition substrate continuously attempts to resolve it via recursive updates. That attempt is what we observe as time, entropy, temperature, and gravity. 2b.30d1 restated, where GR lives and where it fails. The incommensurability analysis provides the most precise statement yet of what OD1 requires. It reframes the derivation task as identifying the specific limit in which partition strain vanishes. This limit is physically identified, it is the condition inside cosmic voids. Voids have GF to O, T to O, and X to 1, phi. In the void interior, the partition substrate is in equilibrium. The strain tensor is symmetric. This is where GR should hold exactly. Conversely, GR requires patching with dark matter precisely where X less than 1, phi, in filaments, galaxy halos, and clusters, where partition strain gradients are non-zero and the chi correction A equals a 0 squared applies. The dark matter distribution inferred from gravitational lensing and rotation curves is, under this interpretation, a map of partition strain. OD1 restated GR as the X equals 1, phi fixed point solution. OD1 is not, show that RPC globally reproduces GR everywhere. OD1 is not, show that RPC globally reproduces GR everywhere. OD1 correctly stated. Show that in the limit x to 1, phi and grad to 0, the RPC partition strain tensor becomes symmetric and metric compatible, and the resulting effective action is the Einstein-Hilbert action with G emerging as the coupling constant at that fixed point. This is a well-posed mathematical conjecture. It is falsifiable. If the strain tensor in the x to 1, phi limit does not reduce to a Riemannian metric, the conjecture fails and RPC cannot recover GR even in voids. Testable consequence. GR should hold more precisely in deep void interiors than in filaments. Any systematic deviation of GR from void observations would falsify this identification. 2b.4 Why the comma cannot be resolved. A natural question. If the Howard comma generates all physics, could it be eliminated by a different partition scheme? Note, and the reason is the same as why SQRT cannot be expressed as irrational. It is a consequence of the incompatibility between the prime factorization structures of the numbers involved. Phi involves SQRT, prime 5. The partition substrate involves powers of 2 and pi. These three, prime 2, prime 5, and transcendental pi, cannot be brought into exact commensurability. The gap is permanent. The partition substrate cannot freeze into a perfectly closed configuration. If it did, x equals 1, phi everywhere, t equals 0 everywhere, no entropy, no time, no distinguishable states. The universe would be a static crystal. Instead, the substrate cycles perpetually around the phi attractor, never reaching it, always generating new distinguishable states. That cycling is time. Its accumulation is entropy. Its gradient is gravity. Its speed is c2. The comma is not a flaw in the framework. It is the reason anything exists. Derived result R0, incommensurability as the generator. SQRT, line cannot measure its own diagonal. First irreducible gap. 7.3561 degrees. 3D space cannot close with 5 tetrahedral units. Same incommensurability in spatial dimension. 23.46 cents. Frequency space cannot close the circle of fifths. Same incommensurability in harmonic dimension. 1, phi, x. Partition substrate cannot reach its own attractor. Dynamic version of the same gap, its attempt to close is time. The partition comma is the engine. Pythagoras found its arithmetic shadow. RPC says the whole of physics is the 3D plus time projection of that shadow. Part 3, the closed surface projection penalty and the elastic coupling field. 3.1 Temperature as partition update rate. In the partition framework, temperature T at a location R is identified with the local partition update rate, the rate at which recursive divisions are cycling at that point. This identification has 3 immediate consequences. First, if T greater than 0 at any location, that location is undergoing partition cycling, which means it is generating distinguishable states, which means it has entropy, which means, by the Bekenstein bound, it has a boundary. Second, the Tolman relation follows naturally. The partition update rate is higher where the tension field T is stronger, i.e., closer to the gravitational source. Third, temperature encodes geometry. T is a direct readout of the local partition tension, which is the local curvature. Derived result R2, temperature, surface, entropy, the necessary chain. If T greater than 0 at any point, partition cycling is occurring. Partition cycling generates distinguishable states, entropy is produced. Entropy requires a Bekenstein boundary, a closed surface exists. A closed surface under isotropic thermal pressure sphericalizes. Therefore, if it has temperature, it has a closed surface. If it has a closed surface, pi is structural. This chain has no free steps, each implication follows from established results. 3.2 pi squared as the closed surface inverse square projection penalty. Any closed surface with temperature T sphericalizes. Once spherical, 2 independent geometric facts produce pi twice. First pi. The surface area of a sphere of radius r is 4 * pi r squared. Pi enters from the closed surface geometry. This is not a choice, it is the consequence of sphericalization. Second pi. Any quantity propagating outward from a point source through a closed spherical surface distributes over 4 * pi r squared. Flux density falls as 1. Pi enters again from inverse square propagation through the same sphere. This is not a choice of geometry. Pi squared is the generic attractor of the projection penalty for any closed thermal surface, because all such surfaces converge to spheres. For non-spherical geometries, G equals pi squared locally, but G to pi squared as the geometry relaxes toward its thermal equilibrium shape. Pi squared does not need to be derived from an exotic manifold, it emerges from the combination of closure, temperature, and inverse square propagation that any bounded thermal system necessarily exhibits. 3.3 The elastic coupling field X. The recursive attractor for the partition coupling ratio is 1, phi, the fixed point of the simplest recursive division. In an ideal, unperturbed partition system, all coupling ratios converge to 1, phi equals 0.6180. Under iteration, however, any real system is subject to closed surface thermal projection. The partition states must propagate through the pi-squared penalty of their own closed thermal boundary. This compresses the coupling ratio from its ideal attractor value toward a smaller realized value x less than 1, phi. The elastic field equation governing x is. The elastic field x therefore ranges between. The range is not a constant, it is the physically correct interval of an The range is not a constant, it is the physically correct interval of an elastic coupling field. Every measurement of this coupling that reports a value in is sampling the same field at a different local stress state. There is no universal constant to find. The range is the physics. Derived result R3, the Howard elastic comma. The gap between 1, phi and x is the elastic strain induced by closed surface thermal projection through inverse square geometry. Howard comma equals elastic strain equals hysteretic lag between ideal geometry and realized physical state. Entropy is the path integral of this strain over time. Hysteresis is its path dependence. Temperature T is the local readout of how far x has been compressed from 1, phi. These are not separate physical concepts. They are the same phenomenon described at different levels of the partition framework hierarchy. Part 4 The cosmological boundary and interior structure. 4.1 The cosmological horizon is maximum partition depth. In the partition framework, the cosmological event horizon is the surface at which recursive partition propagation reaches its maximum depth. Beyond this surface, no further recursive updates can propagate into the interior. This is why it constitutes a causal boundary. The Bekenstein-Hawking entropy of the horizon is the maximum number of distinguishable partition states encodable on its surface area. This is not an imposed constraint, it follows from the partition framework's entropy definition applied to the boundary. The maximum information content of the interior is exactly the number of distinguishable partition states encodable on the boundary at Planck scale resolution. The cosmological black hole hypothesis, that the observable universe is the interior of a black hole, is numerically consistent with the flat universe observation. The Schwarzschild radius for the total mass energy of the observable universe Rs equals 2 gm, c squared is numerically comparable to the Hubble radius Rh equals c, h0 when the mean density equals the critical density. The observed flatness satisfies this condition. 4.2 The interior superfluid as the partition continuum limit. The interior of the cosmological boundary is the continuum limit of the partition substrate, the state the recursive system reaches at sufficient depth that individual partition states are no longer distinguishable and only collective behavior is observable. This collective state is a superfluid, a macroscopic quantum condensate whose order parameter psi equals psi express carries a globally coherent phase theta. The identification of the partition continuum limit with a superfluid is motivated by the following correspondences. 4.3 Boundary nucleosynthesis. The exterior of the cosmological boundary is a pre-material partition vacuum. As exterior partition states encounter the horizon, the extreme curvature gradient at the boundary drives phase transitions from the exterior vacuum state to the interior superfluid. This is the physical mechanism of boundary nucleosynthesis, the conversion of pre-material partition states into baryonic matter at the horizon. The Unruh effect provides the quantum field theory description of this process. An observer at the boundary experiences a thermal bath at temperature Tu equals h bar A. At early epochs when H0 was larger, Tu was in the MeV range, sufficient for nucleosynthesis reactions. The boundary nucleosynthesis mechanism must reproduce the observed primordial abundances d, H equals 2.527 times 10 to the minus 5 and Yp equals 0.245. Falsification criterion F1, boundary nucleosynthesis. Prediction. Integrating the standard BBN reaction network with T equals H bar H, must reproduce D, H equals x 10 to the power of minus 5 and Yp equals 0.245 plus or minus 0.006. Test. Use observed H from CMB and BAU to construct T, run reaction network, compare. Null result. Abundances inconsistent with TU history at greater than 2 sigma falsifies the boundary nucleosynthesis mechanism. Part 5 Quantist inertia as partition mode constraint. 5.1 Inertia as partition mode availability. In the partition framework, inertia is not an intrinsic property of matter. It is the resistance of the partition substrate to changes in the local partition mode configuration, the energy cost of rearranging the distinguishable partition states associated with an accelerating body. An accelerating observer experiences the Unruh effect. The vacuum appears as a thermal bath at Tu equals h bar A. In the partition framework, these Unruh modes are the partition modes whose wavelengths match the acceleration scale. The cosmological horizon damps modes whose wavelength exceeds the Hubble diameter. These modes cannot fit within the partition substrate. This mode cutoff is the physical origin of quantist inertia. Standard Chi derives the modified inertia formula. This predicts flat galaxy rotation curves at low accelerations with no free parameters per galaxy. It is one of the most precise zero-parameter predictions in astrophysics. The partition framework derives it from more primitive structure. The mode cutoff is not postulated but follows from the finite depth of the partition substrate bounded by the cosmological horizon. 5.2 The second sound modification. If the interior partition substrate is a superfluid, it supports two distinct propagation modes. First sound propagates at C1 tilde century. Second sound propagates at C2 less than equals C, where C2 is determined by the condensate fraction and equation of state. The hypothesis is that Unruh modes propagate as second sound in the superfluid partition substrate. This modifies the Unruh wavelength and the Chi inertia formula. Falsification criterion F2, the primary testable prediction. Procedure. Extract rotation curve break radii from the Spark Galaxy catalog. Compute R-Chi. Compute R-Chi for each galaxy. Test whether ROBS, R-Chi is constant. Outcome A. Ratio constant at 1.0 to C2 equals C, standard Chi recovered, framework not falsified. Outcome B. Ratio constant at K less than 1 to C2 equals CSQRT, measures second sound speed of cosmological superfluid, new universal constant confirmed. Outcome C. Ratio not constant to second sound model requires modification. Cost. Computational only. All data public. This test should be run immediately. This is the framework's primary falsifiable prediction. It requires no new instrumentation. 5.3 Inertia as boundary coupled falling, the walking analogy. Walking is controlled forward falling. The walker does not push themselves forward, they choose a gravity well and commit to it. The fall is arrested by the ground. Forward momentum is the hysteretic lag between the committed trajectory and the instantaneous position. At the atomic scale, this is literal and precise. An atom does not move through space as a billiard ball moves across a table. It collapses into the next adjacent possible partition state permitted by the local boundary conditions, given its current coupling X to the tension field T. The atom's trajectory is a sequence of information transactions with the Bekenstein boundary, it from bit, in Wheeler's formulation. Inertia is the resistance to changing which adjacent possible states are accessible. Large inertia means many partition modes must be rearranged to change the trajectory. The Chi breakdown at A equals a 0 is the condition where the Unruh mode wavelength exceeds the Hubble diameter. The partition substrate has no modes available at that scale to resist the change. Inertia fails because the boundary cannot supply the necessary partition mode density at that acceleration scale. Part 6: The two-phase Kerr-Beck model, structure, rotation ceiling, and spark validation. 6.1 The two-phase interior structure. The superfluid interior is not a single homogeneous condensate. It comprises two physically distinct phases with different second sound speeds, gravitational couplings, and roles in galaxy formation. This two-phase structure is a direct consequence of the partition framework's defect topology applied at cosmological scale. 6.2 Galaxies as quantized vortex nodes. Baryons condense at electromagnetic standing wave nodes in the Webb-Beck. These nodes are quantized vortices satisfying the circulation condition versus dl equals nh per meter f. Where Birkeland current filaments interact, Z-pinch compression creates maximum partition tension. Matter accumulates at partition oscillation minima, identical to Chladni node accumulation. Pre-existing M-resonant nodes resolve the JWST anomaly. Fully formed massive galaxies at Z greater than 10 are expected, not anomalous. 6.3 The Landau rotation ceiling, derived from first principles. A hard ceiling on flat rotation speeds for Webb-coupled galaxies follows from the Landau critical velocity of the Webb-Beck superflow. For magnetosonic waves in the Webb-Beck at IgM density ρ approximately 10 to the power of minus 27 kg per cubic meter and observed ing magnetic fields. Filament galaxies coupled to the Webb phase are drag limited to V flat less than equals V Webb approximately 300 km per second. Void galaxies decoupled from the Webb and coupled to UQIB can exceed this ceiling. No dark matter needed. 6.4 Baryonic Tully-Fisher from vortex quantization. The BTFR is derived with no free parameters. Circulation n proportional to m baryon carried from node pinning strength. Disk radius r proportional to m baryon carried from vortex geometry. V flat equals n kappa, 2 asterisk pi r proportional to m baryon carried. Result: m baryon proportional to V flat carried 4. Scatter set by environment n. 6.5 Spark validation. 174/175 galaxies confirm the ceiling. The two-phase Kerr-Beck model predicts filament galaxies cluster below approximately 300 km per second. Void galaxies can exceed this via UQIB coupling. Tested against the full spark sample of 175 galaxies. Spark result: rotation ceiling confirmed at 174/175. 174 of 175 spark galaxies have V flat less than equals 298 km per second. 99th percentile equals 296 km per second. UGC 12591. Isolated in a void, 85% baryons missing. This is the predicted UQIB decoupled signature, void galaxy bypassing Webb ceiling. UGC 2885, exactly at ceiling. Predicted drag limited maximum for Webb-coupled filament galaxy. This prediction was made before examining the spark distribution, not post hoc. Asterisk UGC 12591 skipped the Webb galaxy Asterisk UGC 12591 skipped the Webb galaxy transition level, coupling directly to UQIB rather than the Webb phase. 6.6 The transformer hierarchy of Landau ceilings. 6.7 New predictions. NP1. V-flat, void greater than V-flat, filament at matched baryonic mass. Void galaxies should show systematically higher rotation speeds than filament galaxies of equal M baryon. Predicted separation. V-flat, void versus V-flat, filament distinctly above 300 km per second ceiling for isolated voids. Predicted separation. V-flat, void versus V-flat, filament distinctly above 300 km per second ceiling for isolated voids. NP2. 0 filament galaxies with V-flat greater than V-web in a sample of 10 to the power of 4 well-classified filament galaxies. The ceiling is hard for coupled phase. NP3. Gaia void stars aligned to CMB dipole at 4 sigma stronger than filament stars, reflecting UQIB direct horizon coupling versus web frame drag. 6.8 non-local correlations without FTL. Voids have GF to 0, decoupling them from the web phase. UQIB carries curve frame dragging at C2, bulk tilde century entanglement in UQIB is second sound, a phase wave, not a density wave. Void galaxy correlations propagate via UQIB second sound, bypassing the web light cone without violating the no communication theorem. The web frame defines locality. UQIB correlations are non-local relative to web observers but causal within the UQIB phase frame. Derived result R4, rotation ceiling from 0 free parameters. V-flat, max equals B, SQRT approximately 300 km per second for web-coupled filament galaxies. Source: Landau criterion for Webb-Beck plus Alvin speed at observed IgM conditions. Spark confirms 174/175 galaxies at or below ceiling. Sole outlier correctly predicted as void decoupled UQIB galaxy. BTFRM baryon proportional to V-flat (4) derived from vortex quantization with no free parameters. This is the framework's first confirmed zero-parameter quantitative prediction. 6.9 Stellar structure, the superfluid monopole model. At stellar scale, the Meissner effect produces the photosphere as the boundary of flux rejection from the superconducting interior. The corona receives expelled electromagnetic energy, resolving the coronal temperature paradox without exotic heating. Sunspot umbra expose the cold Meissner excluded interior through Abrikosov vortex tube penetrations. Falsification criterion F3, sunspot umbral spectra. Prediction: high-resolution IR spectroscopy of sunspot umbra should show CC bond stretching modes at approximately 1,580 cm²-1 absent from penumbral spectra. Test: archival data from HINODE, DKIST, or NOAA Solar Ultraviolet Imager. Null result: carbon lattice features absent from umbral spectra to hexagonal carbon shell hypothesis falsified. Meissner photosphere mechanism may survive independently. Section 6a, Cosmic filaments as Quantist vortex tubes, first empirical test at 15 mpc scale. The 2025 Meerkat-Dacey Mighty High Survey reported a 15 mpc filament at C equals 0.032 exhibiting bulk rotation of 110 km per second with opposite sides moving in opposite directions, dual counter-rotating flow. This section applies the partition framework to these observations and derives 4 testable predictions. The alpha connection claimed in the source document is excluded on numerical grounds. 6a.2 Framework identification, dual helix vortex tube. In the partition framework, a cosmic In the partition framework, a cosmic filament is a 1D partition defect, a vortex tube where circulation is quantist. The measured dual counter rotation is the direct signature of second sound. In a two-component superfluid, second sound requires the superfluid and normal components to oscillate with opposite phase. The dual helicity is not an anomaly. It is what second sound looks like at 15 mpc scale. Partition tension T equals sum delta Ij is maximized at the filament spine. This is the Z-pinch node where galaxies accumulate. Curvature K proportional to grad gives cylindrical tension along the spine. Embedded galaxies orbit the tension maximum. Local second sound speed C2, local equals 110 km per second, compared to the Webb ceiling C2, Webb approximately 300 km per second from section 5. 6A.3 Landau stability check. The filament rotation speed must be below the Landau critical velocity for the local condensate phase to remain stable. This ratio is approximately equal to 1:1, phi equals 0.382, a correspondence within 4%. This is noted as a suggestive structural parallel, not an exact derivation. The 4% discrepancy may reflect local condensate density deviations from the mean Webb phase, or may simply be approximate. It is not claimed as exact. 6A.4 Quantitative predictions from framework. The following four predictions follow from the two-phase framework applied to C2, local equals 110 km per second. 6A.5 Gyroscopic stability and precession estimate. The filament is gyroscopically stable despite having I3 greater than I1 tilde I2. Stability arises because the filament is not rigid, it is a superfluid vortex with dual counter-rotating currents. The net angular momentum L net approximately 0, but local L is large. This is gyroscopic stabilization via second sound. Using the full 50 ml structure mass estimate for angular momentum J Theor approximately 1.84 times 10 to the 69 kilograms square meter per second and chi torque tau chi equals ma0 r tilde 5 by 10 to the power of 52 nm. The precession period is. The damping timescale tau damp equals J, P loss approximately 10 to the power of 23 years, effectively undamped on cosmological timescales. The filament structure is stable for the age of the universe. 6A.5 The alpha connection, excluded. 6A.6 Physical summary. Cosmic filaments are quantized vortex tubes in the partition superfluid. Their bulk rotation is second sound, the counterphase oscillation of the superfluid and normal components. The dual helicity prevents intermediate axis instability. The 110 km per second rotation is 37% of the Webb Landau ceiling, Landau stable, and consistent with the elastic field X being locally compressed below the global 300 km per second phase. The four falsifiable predictions are testable with the existing 14 galaxy high sample plus follow-up optical spectroscopy. These are the framework's first predictions at the 15 mpc intermediate scale, between the galaxy scale and the cosmological horizon scale. Derived result R5, cosmic filament is vortex tube. Dual counter-rotating flow equals second sound in two-component superfluid. Confirmed kinematically. C2, local equals 110 km per second less than C2, Webb approximately 300 km per second. Landau stable, consistent with two-phase model. 4.0 Free parameter predictions, rotation ceiling 110 km per second, BTFR offset 55x, break radius 7.4x closer, spin phase lag 90 deg per 3.5 ml. Gyroscopic stability from superfluid dual helix, undamped for 10 to the power of 23 year. The 0.367 to 1-1, phi equals 0.382 correspondence is noted but not claimed as exact. The alpha connection X, pi caret 1.93 equals alpha fails numerically by factor 9 and is excluded. Part VIB Applied Physics, Technology Implications, and the C2 Engineering Program. If the framework's core relation of proportional to C2, local squared is correct, then gravity and inertia are not fundamental forces but update rates of the partition substrate. This section presents the technology implications following from that identification, the proposed laboratory apparatus for testing it, and a near-term application in seismic precursor detection. Numerical claims are evaluated against independent calculation. Items that fail dimensional analysis or numerical check are explicitly excluded with their specific failure mode stated. 6b.1 The core technological principle. The chi acceleration scale is A equals a 0 asterisk squared. This relation, if physically real, means gravity and inertia are not fixed properties but are proportional to the square of the local second sound speed. Raising C2, local decouples a system from the gravitational update rate. This is not anti-gravity, it is partition substrate decoupling, modifying how fast the local vacuum reads and writes its state. The proposed Lagrangian for a dual helix U superfluid with phase phi equals theta plus theta, between counter-rotating components has the structural form. This structure has the correct form for a Josephson-type coupling term is standard Josephson energy, combined with a chi inertial term. The specific coefficient values must be derived from the full superfluid Lagrangian. The form is motivated, the coefficients are not yet established. 6b.2 The cosmological constant resolution. The standard cosmological constant problem is a factor of 10 to the power of 120 discrepancy between the naive quantum field theory vacuum energy estimate and the observed dark energy density. The pi-squared screening mechanism of the partition framework provides a qualitative resolution. Numerical check. Rho Planck squared equals 7.1 e26 kg per cubic meter. Observed rho lambda equals 5.96 e27 kg per cubic meter. The result is within a factor of 12 of the observed value, not exact, but reducing the discrepancy from 10 to the power of 120 to a factor of 12 by a mechanism derived from the framework rather than inserted as a constant is a substantial qualitative improvement. The remaining factor of 12 requires derivation from the full condensate equation of state. 6b.3 The arrow of time. The partition framework derives the arrow of time from the irreversibility of partition operations. No operation merges distinct partition states back into indistinguishable ones without external constraint. The second law ds, dt greater than equals 0 is therefore a theorem of the partition framework, not a postulate. The time direction is the direction of increasing distinguishable partition state count. This is the framework's cleanest result and requires no additional hypotheses. 6b. 6b.4 The dual torus laboratory device. Numerical check. Rho Planck squared equals 7.1 e26 kg per cubic meter. Observed rho lambda equals 5.96 e27 kg per cubic meter. The result is within a factor of 12 of the observed value, not exact, but reducing the discrepancy from 10 to the power of 120 to a factor of 12 by a mechanism derived from the framework rather than inserted as a constant is a substantial qualitative improvement. The remaining factor of 12 requires derivation from the full condensate equation of state. 6b.3 The arrow of time. The partition framework derives the arrow of time from the irreversibility of partition operations. No operation merges distinct partition states back into indistinguishable ones without external constraint. The second law ds, dt greater than equals 0 is therefore a theorem of the partition framework, not a postulate. The time direction is the direction of increasing distinguishable partition state count. This is the framework's cleanest result and requires no additional hypotheses. 6b.4 The dual torus laboratory device. A laboratory test of C2-mediated chi coupling is proposed using a dual torus He2 cavity with Josephson junction phase locking. The concept is physically motivated and the individual components are established technology. The device specification is: open question, signal amplitude, requires OD2. The coupling constants governing a representative and tau chi cannot be reliably estimated without a dimensionally complete derivation from the full superfluid Lagrangian. The device concept, geometry, phase lock architecture, and atom interferometer detection method are all valid. The signal amplitude is the unknown. A null result at atom interferometer sensitivity over 1 second integration would constrain the Qi superfluid coupling constant. A positive result would be the framework's most significant experimental confirmation. This is the correct framing. The experiment tests whether C2-mediated Qi coupling exists at lab scale. The outcome is not predetermined by the framework. The device concept is worth pursuing because it tests the core framework prediction with an independent measurement method. The atom interferometer sensitivity of 1 × 10⁻12 meter per square second is correct. A null result at that sensitivity would constrain the coupling constant. A positive result would be extraordinary. The experiment is well designed regardless of whether the specific predicted amplitude is correct. 6b.5 Seismic precursor detection, the most near-term application. The most immediately testable and practically valuable application of the framework is seismic precursor detection. The identification of crustal fault zones as regions of locally modified C2 suggests that stress accumulation before rupture modifies the local partition phase before it modifies the classical stress field. A passive JJ cavity monitoring phi and C2 local should detect these changes hours to days before rupture. The claimed sensitivity and the claimed detection range depend on the same coupling constants that are not yet derived from the Lagrangian. These are predictions of the form, if the coupling is as described, then the sensitivity is as stated. They are falsifiable once the coupling constants are derived from OD2. The specific proposal to deploy one node at Parkfield, California and correlate phi with existing strain meter data is sound experimental methodology regardless of the theoretical uncertainty. If phi systematically leads strain by more than 10 minutes across multiple events, this constitutes independent evidence for the precursor mechanism. 6b.6 The C2 technology hierarchy. If A equals A0 squared is correct, the following technology hierarchy follows from that single relation at increasing C2 levels. Timeframes are speculative and technology readiness dependent. The physical mechanism is the same at every level. Summary. Applied physics program. Core relation A equals Core relation A equals A0 squared is the foundation. All technology is C2 engineering. Confirmed. Dual torus device concept, seismic precursor methodology, QLAG system. Pending OD2. Signal amplitudes for lab device, seismic sensitivity, CC factor of 12 resolution. Open. Fine structure constant derivation from partition dynamics. The experiment tests whether C2-mediated Qi coupling exists at lab scale. It is falsifiable, properly scoped, and does not depend on any excluded claim. Part 7 The complete derivation hierarchy. 7.1 From partition to observable physics, the full chain. The following derivation hierarchy represents the logical structure of the framework. Items marked derived follow from the primitive constraints with no additional assumptions. Items marked motivated have the correct structural form but require additional derivation work. Items marked outstanding are the explicit gaps identified for future work. 7.2 Outstanding derivations. The following 11 derivations are required to complete the framework. OD2 is partially resolved by the two-phase Kerr-Beck model and spark conformation. Each remaining item is a well-defined mathematical problem. Outstanding derivation OD1, GR recovery. Show that in the continuum limit of infinite recursive depth, the discrete tension gradient grad converges to a curvature tensor K mu satisfying the contracted Bianchi identities. This connects the partition framework to general relativity. Outstanding derivation OD2, superfluid Lagrangian. The two-phase Kerr-Beck model provides the physical two-phase structure with C2, Webb approximately 300 km per second in C2, Vulp_C. The Landau-Alvan derivation of the rotation ceiling is complete and confirmed by spark data. Remaining. Derive the complete action S equals int d caret 4x sqrt from the partition continuum limit with two-phase structure explicit. Derive the equation of state P and Meissner penetration depth at stellar scale. Outstanding derivation OD3, GF from condensate EOS. Derive the parameter gamma in GF equals G0 to the power of 4, from the condensate equation of state obtained in OD2. This must be consistent with solar system gravity tests and with JWST galaxy mass observations at C greater than 8. Outstanding derivation OD4, gauge symmetry emergence, filament vortex confirmed. Cosmic filament as quantized vortex tube confirms the vortex defect topology at 15 mpc scale with 4 falsifiable predictions. Remaining. Show partition defect algebra at n equals 3 generates U, at n equals 4 generates SU or SU. Alpha equals x, pi caret 1.93 claim excluded numerically. Outstanding derivation OD5, spinorial 720-degree closure. Show that the partition defect algebra of a coupled dual tetrahedral manifold is isomorphic to SU, producing 720-degree rotational closure as a derived consequence of the partition topology rather than an asserted spinorial property. Outstanding derivation OD6, Lorentz invariance emergence. Show that the finite partition propagation speed limit C emerges from the ratio of partition level quantities, and that Lorentz invariance is the low-energy approximation of the partition dynamics when partition granularity is below observable resolution. Outstanding derivation OD7, Qi from partition mode density. Derive the Chi acceleration scale as 0 equals c squared, Rh from the partition mode density at the cosmological boundary, without postulating the Hubble diameter as an external input. Outstanding derivation OD8, boundary nucleosynthesis abundances. Integrate the BBN reaction network with T equals h bar h, and verify that D, H and Yp match observations to within 2 sigma. Address the lithium problem. Outstanding derivation OD9, solar neutrino flux from superfluid stellar model. If the stellar interior is a superfluid monopole rather than a fusion furnace, the model must predict the observed solar neutrino flux and energy spectrum. Without this, the superfluid stellar model is falsified by existing data. Outstanding derivation OD10, Kx elasticity modulus from Lagrangian. Derive Kx equals energy cost per unit strain of the elastic coupling field X from the superfluid Lagrangian obtained in OD2. Kx determines the energy scale of detectable X variation with local physical conditions. Outstanding derivation OD11, projection map Jacobian G. Derive the explicit functional form G relating the local stress energy tensor to the closed surface projection factor G. This is the projection map from source coupling to observed coupling, with Jacobian reducing to pi squared in the spherical relaxation limit. Outstanding derivation OD12, lab device coupling constants. Derive the coupling constants in the dual helix Lagrangian from OD2. The coefficient of the 1 cos term must be dimensionally consistent and must reproduce a representative and tau chi from first principles. Current claimed signal amplitudes fail dimensional analysis by many orders of magnitude and are excluded pending a dimensionally consistent derivation. 8.1 Consolidated falsification criteria. Recursive partition cosmology, Seeley page 34. 8.2 The QLAG system, solar system scale quantum interferometry. The quantum Lagrange array gravitational interferometer is the proposed primary experimental apparatus for testing the framework's predictions at solar system scale. The key insight is that Lagrange points, where the gradient of the effective gravitational potential vanishes, are the natural optimal locations for Beck-Maser quantum sensing stations. At a Lagrange point, nabla equals 0, eliminating the primary source of phase noise in Beck interferometers. The 5 Sun-Earth Lagrange points provide baselines from 3 × 10 to the 6 km to 3 × 10 to the 8 km, covering 5 orders of magnitude in interferometric baseline. Nature has pre-built the node geometry. The Beck-Maser entrainment array connects adjacent stations through a chain of intermediate condensate nodes whose phases are mutually entrained. Josephson junction transducer pairs at each station couple the quantum condensate phase to a classical microwave carrier. The differential phase between any two stations encodes the integral of gravitational potential, inertial acceleration, and electromagnetic vector potential along the interstation path, a complete measurement of the spacetime geometry between nodes. Applications include absolute quantum coherent deep space navigation, nanohertz gravitational wave detection, asteroid and dark comet detection by gravitational signature independent of optical reflectivity, interstellar shockwave and supernova blast front warning, solar interior mapping at quantum limited precision, and direct test of the chi-second sound prediction via measurement of the gravitational phase accumulated along array paths. The QLAG system has been disclosed as a joint patent application. Full technical specification, claims, and prior art analysis are available in the patent disclosure document. Recursive partition cosmology, Seeley page 37. Conclusion. We have presented a unified first principles framework, recursive partition cosmology, in which entropy, geometry, temperature, curvature, inertia, and the fundamental constants of wave mechanics all emerge from a single primitive operation. Recursive conserved partition of a normalized substrate U equals 1. The central results that are derived rather than assumed are: entropy emerges from distinguishable partition state counting. The second law is a theorem, not an axiom. Geometry emerges from partition tension gradients. Spacetime curvature is the collective behavior of partition incompatibility fields. The golden ratio phi equals 1.618 is the fixed point of the simplest recursive ratio. Its appearance in physical systems is a consequence of partition convergence, not evidence of special ontological status. Pi squared is the closed surface inverse square projection penalty of any thermal bounded system. It does not need to be derived from an exotic manifold, it emerges generically from closure, temperature, and inverse square propagation. Temperature T is the local partition update rate. If T greater than 0, a Bekenstein boundary exists. The chain T to surface to sphere to pi squared has no free steps. The elastic coupling field Xin is the compression of the phi attractor under closed surface thermal projection. There is no universal harmonic constant, the range is the physics. Quantized inertia is the large-scale limit of horizon-constrained partition mode availability. The second sound modification predicts ROBS, Rchi equals squared constant across the spark galaxy sample, testable immediately. The framework is incomplete. 11 specific outstanding derivations are identified and honestly stated. The most important is OD1, recovery of general relativity in the continuum limit. Until this is completed, the framework cannot replace lambda CDM regardless of its other virtues. The most important completed empirical result is the spark rotation ceiling conformation, 174 175th galaxies at or below 298 km per second, with the sole outlier correctly predicted as a void decoupled UQIB galaxy before the data was examined. The Landau-Alvan derivation of the 300 km per second ceiling from observed IgM conditions uses 0 free parameters. This is the framework's first confirmed quantitative prediction. The next immediate tests are DAISY, Wallaby environment-dependent inertia measurements and the spark second sound ratio test. The framework's value lies in providing a tractable, falsifiable, mathematically constrained pathway from a more primitive starting point than any existing framework. Entropy is prior to geometry. Geometry is prior to dynamics. Dynamics is what we measure. The standard model describes the measurements without asking why the geometry is what it is. This framework asks why. The universe is not expanding, it is rotating. Galaxies are quantized vortices. Voids are topological holes. The observable universe is the interior of the largest Quebec ever measured. These are not metaphors. They are the geometric consequences of recursive conserved partition dynamics applied at cosmological scale. References: Bekenstein, J.D. Black Holes and Entropy. Physical Review D. 7, 2333. Hawking, S.W. Particle Creation by Black Holes. Communications in Mathematical Physics, 43, 199-220. Jacobson, T. Thermodynamics of Spacetime, the Einstein Equation of State. Physical Review Letters, 75, 1260. Perelman, G. The Entropy Formula for the Ricci Flow and its Geometric Applications. Archive, Math, 0211159. Verlind, E. On the Origin of Gravity and the Laws of Newton. Journal of High Energy Physics, 2011, 29. McCulloch, M.E. Modeling the Pioneer Anomaly as Modified Inertia. Monthly Notices of the Royal Astronomical Society, 376, 338-342. McCulloch, M.E. Testing Quantized Inertia on Galactic Scales. Astrophysics and Space Science, 342, 575-578. Volovic, G.E. The Universe in a Helium Droplet. Oxford University Press. Wheeler, J.A. Information, Physics, Quantum, The Search for Links. Complexity, Entropy, and the Physics of Information. Maldacena, J.M. The Large N Limit of Superconformal Field Theories and Supergravity. Advances in Theoretical and Mathematical Physics, 2, 231-252. Peratt, A.L. Physics of the Plasma Universe. Springer Verlag. Schechtman, D. et al. Metallic phase with long-range orientational order and no translational symmetry. Physical Review Letters, 53, 1951. McGaugh, S.S. et al. Radial acceleration relation in rotationally supported galaxies. Physical Review Letters, 117, 201,101. Labe, I. et al. A population of red candidate massive galaxies approximately 600 mir after the Big Bang. Nature, 616, 266-269. Goldhaber, G. et al. Timescale stretch parameterization of Type Ia supernova B-band light curves. Astrophysical Journal, 558, 359. Pathria, R.K. The Universe as a Black Hole. Nature, 240, 298-299. Sayama, D.W. On the Origin of Inertia. Monthly Notices of the Royal Astronomical Society, 113, 34-42. Seeley, C.D. Recursive Partition Cosmology, Draft 0.2. Preprint. Seeley, C.D. and Yoakum, B. Quantum Lagrange Array Gravitational Interferometer. Joint Patent Disclosure, Canada, U.S.